The real Silurian hypothesis. Could we detect ancient industrial civilizations? Part 1. In 2018, something unusual happened in the world of climate science. Two respected researchers, Gavin Schmidt from NASA's Goddard Institute and Adam Frank from the University of Rochester, published a paper that would make people think differently about our planet's deep history. They weren't claiming to have found evidence of ancient aliens or lost civilizations buried in Earth's rocks. Instead, they asked a deceptively simple question that would challenge how we think about detecting technological civilizations anywhere in the universe. If an industrial civilization had existed on Earth millions of years before humans evolved, would we actually be able to find any trace of it today? This question emerged from their climate research, where they were documenting how human industrial activity is creating what geologists call the Anthropocene, a new geological epoch defined by human impact on Earth's systems. As they studied the chemical signatures our civilization is embedding in ice cores, sediment layers, and atmospheric composition, they realized they were essentially creating a blueprint for how future scientists might detect our existence millions of years from now. This led them to wonder whether similar signatures from hypothetical ancient civilizations might be hiding in plain sight within Earth's geological record. They named their thought experiment the Silurian Hypothesis, borrowing from the intelligent reptilian species in Doctor Who that supposedly evolved on Earth before humans. But this wasn't science fiction speculation. This was rigorous scientific inquiry using established methods from geology, atmospheric chemistry, and paleoclimatology to explore what traces advanced technology might leave behind and whether we'd recognize them after millions of years of geological processes had obscured or transformed the evidence. The challenge of detecting ancient civilizations becomes clear when you consider the immense scale of geological time. Earth formed 4.54 billion years ago, and complex life has existed for roughly 550 million years. Human industrial civilization began about 300 years ago during the Industrial Revolution. If you compressed Earth's entire history into a single year, our industrial civilization would have existed for less than 2 seconds on December 31st. Finding evidence of a brief technological phase that occurred millions of years earlier would be like searching for a specific 2-second moment that happened months ago in that compressed timeline. Most evidence of civilizations disappears remarkably quickly when measured against geological time. Buildings crumble and erode within thousands of years, returning their materials to natural sediment cycles. Metals oxidize back into mineral forms that become indistinguishable from naturally occurring ores. Organic materials decompose completely, broken down by bacteria and chemical processes that leave no trace of their artificial origins. Even plastic, which seems permanent from our perspective, may break down over millions of years through photodegradation, thermal decomposition, and biological processes we're only beginning to understand. Yet certain types of evidence might persist across vast spans of time, preserved in the geological record like pages in Earth's history book. Chemical signatures embedded in rock layers could survive indefinitely, particularly isotopic ratios that differ from natural background levels. Changes to atmospheric composition might be preserved in ice cores from polar regions or in the chemical composition of ancient soils. Large-scale modifications to Earth's surface chemistry could leave traces in sediment cores taken from deep ocean basins where materials accumulate slowly over millions of years. Mass extinction events recorded in the fossil record might preserve evidence of rapid environmental changes that accompanied technological activity. To understand what signatures ancient civilizations might have left behind, Schmidt and Frank first had to catalog what signatures our own civilization is currently creating. Modern industrial activity produces distinctive atmospheric changes that will be clearly visible to future geologists. Carbon dioxide levels have increased by more than 40% since pre-industrial times, creating isotopic signatures in atmospheric carbon that result from burning fossil fuels that were locked underground for millions of years. Methane concentrations have doubled due to agriculture and industrial processes. We've introduced entirely artificial chemicals like chlorofluorocarbons that don't occur anywhere in nature and will persist in the atmosphere for decades or centuries. Our chemical footprint extends far beyond greenhouse gases. Industrial processes distribute heavy metals globally through atmospheric transport, creating pollution signatures that will be preserved in sediment layers. We produce synthetic nitrogen through the Haber-Bosch process for fertilizers, altering the global nitrogen cycle and creating isotopic ratios that differ from natural biological nitrogen fixation. Nuclear weapons testing has scattered artificial radioactive isotopes throughout the environment, creating signatures that will remain detectable for thousands of years. Plastic production creates microscopic particles that are spreading throughout oceanic and terrestrial environments, potentially creating a distinctive marker layer in future sediment cores. We're also causing biological changes on a scale comparable to major geological extinction events. The current mass extinction rivals the Great Dying that occurred 252 million years ago, eliminating species at rates far above natural background levels. We've introduced species to new continents, mixing biogeographical regions that were separated for millions of years. Selective breeding has created new varieties of plants and animals that carry genetic signatures of human intervention. These biological modifications will leave clear traces in the fossil record that future scientists would easily recognize as evidence of technological intervention in natural evolutionary processes. The physical modifications we're making to Earth's surface represent another category of potentially preserved evidence. Large-scale mining operations are altering the mineral composition of surface materials in ways that might remain detectable millions of years from now. We're creating new materials like concrete and steel alloys that have chemical compositions unlike anything produced by natural geological processes. Massive construction projects are modifying landscapes on scales that might leave geometric patterns visible in future geological surveys. Even our artificial lighting is changing Earth's energy balance in ways that might be detectable from space. But would these signatures actually survive millions of years of geological processing? And would future scientists recognize them as evidence of ancient technology? This question reveals the core challenge of the Silurian hypothesis. Carbon isotope anomalies from fossil fuel burning might persist in sediment layers, creating chemical signatures that future geologists could detect as evidence of massive, rapid carbon release from underground reservoirs. However, natural processes like volcanic eruptions and methane releases from ocean sediments can create similar isotopic signatures, making it difficult to distinguish artificial from natural carbon cycle disruptions. Plastic particles might survive in deep ocean sediments or other protected environments where chemical breakdown occurs slowly. These microscopic fragments could create a distinctive marker layer that future scientists would recognize as evidence of artificial polymer production. The global distribution of plastic particles and their resistance to natural degradation processes would provide strong evidence for worldwide industrial activity during a specific geological period. The mass extinction we're currently causing will certainly appear in the fossil record as a dramatic biodiversity loss event. However, natural mass extinctions have occurred multiple times in Earth's history due to asteroid impacts, volcanic eruptions, and climate changes. Future paleontologists might struggle to distinguish between extinction events caused by technological civilizations and those resulting from natural catastrophes, particularly if the technological signatures had degraded over millions of years. Nitrogen isotope changes from industrial fertilizer production might persist in certain sediment environments, but biological nitrogen fixation also creates isotopic variations that could mask artificial signatures. The challenge lies in recognizing patterns that clearly indicate coordinated, global-scale technological intervention rather than natural variations in biological and geological processes. When scientists began searching Earth's geological record for signatures that might indicate previous industrial civilizations, they found no convincing evidence. Every anomalous chemical signature, unusual extinction pattern, or rapid environmental change that initially seemed mysterious has been explained through natural geological, biological, or astronomical processes. The Paleocene-Eocene thermal maximum, which occurred 56 million years ago, initially appeared to show rapid atmospheric changes similar to what human industrial activity produces. However, detailed analysis revealed that massive volcanic activity and natural methane releases could explain the event without requiring technological intervention. This absence of evidence is scientifically valuable because it demonstrates that our methods for detecting artificial signatures work correctly. We can distinguish between natural and technological processes when we have sufficient data and appropriate analytical techniques. The fact that we find no evidence for ancient civilizations increases our confidence that the dramatic environmental changes we observe in the geological record resulted from natural processes rather than unknown technological activities. The search for ancient Earth civilizations also revealed how sophisticated natural processes can be in creating chemical signatures that might initially appear artificial. Volcanic eruptions can rapidly change atmospheric composition, create unusual isotopic ratios, and distribute rare elements globally in patterns that might seem to indicate industrial activity. Biological evolution can produce dramatic changes in ecosystem composition that leave extinction signatures in the fossil record. Climate feedbacks can create rapid environmental transitions that affect global chemistry and biology in ways that might appear coordinated if we didn't understand the underlying natural mechanisms. The implications of the Silurian hypothesis extend far beyond questions about Earth's history. If industrial civilizations leave only subtle chemical traces that fade over millions of years, this fundamentally changes how we should search for evidence of technological activity on other worlds. Rather than looking for obvious signs of construction or communication, we might need to focus on detecting atmospheric pollution, unusual isotopic ratios, or rapid environmental changes that could indicate technological intervention in planetary systems. The hypothesis also relates to the Fermi Paradox, which asks why we haven't encountered evidence of extraterrestrial civilizations despite the apparent likelihood that they should exist. If technological phases are brief compared to biological evolution, and if the signatures of technology fade quickly after civilizations end or advance beyond detectable industrial activity, then the universe might be filled with worlds that have hosted technological civilizations without leaving traces we can currently detect. From an astrobiology perspective, the Silurian hypothesis suggests that we should search for signs of current technological activity rather than evidence of past civilizations. Atmospheric pollutants, artificial lighting, or large-scale environmental modifications might be detectable on nearby exoplanets using next-generation space telescopes. However, civilizations that ended millions of years ago or that advanced beyond industrial technology might be essentially invisible to our current detection methods. The research inspired by the Silurian hypothesis has improved our understanding of how to identify artificial signatures in natural systems, how chemical and biological evidence is preserved across geological time, and what kinds of processes can cause rapid environmental changes. Even though the search for ancient Earth civilizations yielded negative results, the methodologies developed during this research are now being applied to analyze exoplanet atmospheres and search for signs of technological activity around other stars. Perhaps the most important insight from the Silurian hypothesis concerns our own civilization's long-term impact and responsibilities. The research reveals which of our activities will leave permanent traces in Earth's geological record and how future scientists will interpret our era millions of years from now. Our industrial civilization is creating signatures that will persist long after our buildings crumble and our electronic devices decay. The atmospheric chemistry changes, mass extinction event, and artificial materials we're producing will serve as permanent markers of our existence and our impact on planetary systems. This geological perspective forces us to think about our civilization's legacy across timescales that dwarf human history. The signatures we're creating today will be studied by whatever intelligences examine Earth's geological record millions of years from now. The choices we make about energy systems, environmental management, and technological development will echo through deep time, potentially serving as either warnings about the dangers of unsustainable technology or examples of how civilizations can successfully navigate the transition to long-term sustainability. The Silurian hypothesis represents science at its best, taking an imaginative question and subjecting it to rigorous analysis using established methods and evidence-based reasoning. While the search revealed no evidence for ancient Earth civilizations, it provided invaluable insights into planetary system evolution, technological signature detection, and our own civilization's place in the cosmic context. The negative results don't make the research worthless. They make our understanding of natural processes stronger and our methods for detecting truly artificial signatures more reliable. As we continue to search for signs of life and intelligence elsewhere in the universe, the lessons learned from the Silurian hypothesis will guide our efforts. We now understand better what kinds of signatures technological civilizations produce, how long these signatures might persist, and how to distinguish between natural and artificial processes in planetary systems. Whether or not we ever find evidence of extraterrestrial technology, the Silurian hypothesis has already succeeded in expanding our understanding of how intelligence and technology interact with planetary evolution across the vast scales of geological time. The real Silurian hypothesis, Technosignatures and the Search for Alien Civilizations Part 2. The Silurian hypothesis began as a simple question about whether we could detect ancient civilizations on Earth, but it evolved into something far more significant. When scientists realized they were learning how to identify technological signatures in planetary systems, they understood they had developed a powerful new approach to one of humanity's most profound questions. Are we alone in the universe? The methods developed to search for hypothetical ancient Earth civilizations are now being used to search for signs of alien technology among the stars, revolutionizing our approach to the search for extraterrestrial intelligence. Traditional efforts to find alien civilizations focused primarily on detecting artificial radio transmissions, following the assumption that advanced civilizations would communicate using electromagnetic signals that we could intercept with radio telescopes. The Silurian hypothesis expanded this approach dramatically by asking what other signs of technology might be detectable across interstellar distances. If we could identify the chemical, atmospheric, and physical signatures that technological civilizations leave in planetary systems, we might be able to detect alien technology even if they weren't actively trying to communicate with us. This insight led to the development of what scientists now call technosignature research, the systematic search for any evidence of technology in astronomical observations. Unlike traditional SETI's focus on intentional communication signals, technosignature research looks for the inevitable byproducts of technological activity, the signatures that civilizations produce simply by existing and using energy to support their populations and infrastructure. The first step in developing technosignature detection methods involved understanding what signatures our own civilization produces that might be detectable from other star systems. Human industrial activity creates distinctive atmospheric modifications that could be observed by alien astronomers studying Earth's atmosphere. Our greenhouse gas emissions have altered atmospheric chemistry in ways that produce isotopic signatures clearly indicating fossil fuel combustion. We've introduced synthetic chemicals like chlorofluorocarbons that don't occur naturally anywhere in the universe and represent unambiguous evidence of industrial chemical production. Our cities create artificial lighting that changes Earth's thermal signature and would be detectable as geometric patterns of illumination on the planet's night side. Large-scale construction and mining operations modify surface reflectivity and create landscape patterns visible from space. Agricultural activities create geometric field boundaries and seasonal vegetation changes that indicate coordinated land management on continental scales. All of these signatures could theoretically be detected by sufficiently advanced alien technology observing Earth from nearby star systems. The challenge of detecting these signatures on distant planets pushes current technology to its absolute limits and beyond. With existing instruments, we can barely detect the basic atmospheric compositions of large planets orbiting close to their stars, and even this requires ideal observing conditions and sophisticated data analysis techniques. Detecting trace atmospheric pollutants that might indicate industrial activity requires sensitivity improvements of several orders of magnitude beyond our current capabilities. The signal-to-noise problem represents perhaps the greatest technical challenge in technosignature detection. Industrial pollutants typically represent tiny fractions of total atmospheric composition, often measured in parts per million or billion. Natural atmospheric processes create chemical variations that can mask artificial signatures, requiring extremely precise measurements to distinguish between natural variability and technological modification. Surface changes from construction or mining might affect only small percentages of planetary surfaces, making them difficult to detect against the natural diversity of geological features. Despite these challenges, several detection strategies show genuine promise for identifying extraterrestrial technosignatures. Atmospheric disequilibrium represents one of the most promising approaches, focusing on atmospheric compositions that can't be maintained by natural processes alone. Certain combinations of gases, particularly reactive species that should rapidly combine or decompose in planetary atmospheres, might indicate active technological production or management systems. Industrial pollutants offer particularly compelling targets for detection because many synthetic chemicals have no natural sources anywhere in the universe. Chlorofluorocarbons provide an excellent example of ideal technosignature compounds because they're completely artificial, extremely stable in planetary atmospheres, and were produced by human civilization in quantities that would be detectable from interstellar distances using sufficiently sensitive instruments. Current projects are developing the spectroscopic sensitivity needed to detect CFC-level signatures in the atmospheres of nearby rocky planets. The search for megastructures represents another major branch of technosignature research, based on the idea that advanced civilizations might build massive engineering projects to harness stellar energy. Freeman Dyson proposed that sufficiently advanced civilizations might construct structures around their stars to capture significant fractions of stellar energy output, creating detectable signatures in the form of unusual stellar dimming patterns or excess infrared radiation from waste heat. Several astronomical objects have generated excitement as potential megastructure candidates, most famously Tabby's star, which shows irregular dimming patterns up to 22% that are difficult to explain through known natural phenomena. While most astronomers favor natural explanations involving unusual dust clouds or stellar variability, these objects demonstrate that current telescopes have the sensitivity to detect large-scale stellar engineering projects if they exist. The connection between technosignature research and the Fermi Paradox has become increasingly important as our understanding of detection challenges has improved. The Fermi Paradox asks why we haven't encountered evidence of extraterrestrial civilizations despite the apparent likelihood that they should exist in a universe containing billions of potentially habitable planets. Technosignature research reveals that detecting alien civilizations may be far more difficult than previously assumed, potentially explaining why the universe appears so quiet despite its vast size and age. Industrial phases of technological development might be extremely brief compared to biological evolution timescales, creating narrow windows of detectability that we might easily miss. Most technosignatures may fade quickly after civilizations end their industrial phases or advance to more sophisticated technologies that don't produce detectable waste signatures. Advanced civilizations might develop energy systems that don't produce excess heat, transportation methods that don't require massive infrastructure, or communication technologies that don't leak detectable signals into space. The possibility that natural processes can mimic artificial signatures represents a crucial challenge that emerged from Silurian Hypothesis research. Volcanic activity can produce unusual atmospheric compositions and rapid chemistry changes that might initially appear to indicate industrial activity. Biological processes in extreme environments can create chemical signatures that seem to require technological production. Stellar variability and cosmic ray interactions can drive atmospheric changes that mimic the effects of technological atmospheric management. This recognition of natural mimics has led technosignature researchers to emphasize the importance of multiple independent lines of evidence for any potential detection. Confident identification of alien technology will require several different types of signatures pointing toward the same conclusion: evidence that natural processes cannot explain the observations, and patterns consistent with intentional technological activity rather than random natural variation. The development of next-generation detection technologies promises dramatic improvements in technosignature detection capabilities. The James Webb Space Telescope represents a major advance in our ability to analyze exoplanet atmospheres, with sensitivity sufficient to detect some types of industrial pollutants in the atmospheres of nearby rocky planets. Proposed future space missions include large interferometers specifically designed for direct exoplanet imaging and specialized technosignature detection satellites that could monitor thousands of star systems simultaneously. Artificial intelligence applications are revolutionizing technosignature research by enabling analysis of massive astronomical datasets for subtle patterns that might indicate technological activity. Machine learning algorithms can distinguish weak artificial signals from natural background variations, predict new types of technosignatures to search for, and coordinate observations across multiple instruments and wavelengths automatically. The philosophical implications of technosignature research extend far beyond technical detection methods. The search forces us to confront fundamental questions about the nature of intelligence, technology, and our place in the cosmic community. Current technosignature searches necessarily assume that alien civilizations follow similar technological development paths as humans, create similar environmental impacts during their industrial phases, and use energy in ways that produce detectable waste signatures. These assumptions may be incorrect, potentially making most alien civilizations invisible to our current search methods. Intelligence might develop along pathways completely different from human technological development, creating signatures we wouldn't recognize as evidence of technology. Advanced civilizations might achieve energy and material systems that operate through physical principles we don't yet understand, making their activities undetectable to our current science. The ethical dimensions of technosignature detection raise important questions about how humanity should respond to potential discoveries. Should we actively advertise our presence to potentially superior civilizations by increasing our own technosignature production? What responsibilities might we have if we detected struggling civilizations facing environmental collapse? How should human society prepare for the possibility of confirmed alien technology detection? Research inspired by the Silurian Hypothesis also provides crucial insights into our own civilization's future trajectory and cosmic responsibilities. Analysis of human technosignatures reveals concerning patterns of rapid environmental modification, increasing production of persistent artificial materials, and growing energy consumption that may not be sustainable over geological timescales. The perspective gained from studying our signatures from a cosmic viewpoint highlights questions about what kind of technological civilization we want to become. Multiple ongoing research programs are actively searching for technosignatures using methods developed from Silurian Hypothesis research. NASA has begun funding technosignature research as a legitimate scientific endeavor, supporting development of new detection methods and searches for atmospheric pollutants on exoplanets. The SETI Institute has expanded beyond radio signal searches to investigate rapid transient phenomena, artificial lighting signatures, and coordination with exoplanet discovery missions. Universities worldwide contribute specialized expertise in atmospheric chemistry, stellar engineering detection, and pattern recognition in astronomical datasets. The next decade should bring significant developments in technosignature detection capabilities, including the first confirmed atmospheric analyses of rocky planets in habitable zones, improved sensitivity to trace atmospheric components that might indicate technology, and better understanding of natural processes that can mimic artificial signatures. We may witness the detection of our first confirmed extraterrestrial technosignature, fundamentally changing humanity's understanding of our place in the universe. Even if technosignature searches continue to yield negative results, the research provides valuable insights into planetary system evolution, the rarity of technological civilizations, and the challenges facing any species attempting to develop sustainable technology. Every planet we examine and find devoid of technosignatures tells us something important about how common or rare technological development might be in the universe. The Silurian Hypothesis has evolved from a thought experiment about ancient Earth civilizations into a comprehensive scientific framework for understanding technology's role in planetary evolution and cosmic development. While we found no evidence for previous technological civilizations on Earth, the search itself revolutionized our approach to detecting intelligence throughout the universe. The methods developed to search for hypothetical ancient civilizations are now being applied to examine hundreds of exoplanets for signs of current technological activity. Each negative result refines our understanding of natural planetary processes and improves our ability to recognize truly artificial signatures when we encounter them. The absence of detected technosignatures so far may indicate that technological civilizations are rare, that industrial phases are brief, or that we're searching for the wrong kinds of signatures. Our own civilization's technosignature production places us in a broader cosmic context where we might be observable to alien astronomers using methods similar to those we're developing to search for them. The atmospheric modifications, artificial lighting, and surface changes we're creating will remain detectable for millions of years, potentially serving as beacons for other civilizations to discover long after our current technological phase ends. The ultimate significance of technosignature research may lie not in what we discover about alien civilizations, but in what we learn about the challenges and responsibilities facing any technological species. The search for ancient Earth civilizations revealed that sustainable technology development represents a critical challenge that determines whether civilizations survive long enough to leave lasting signatures in their planetary systems. As our detection capabilities continue to improve and our catalog of analyzed exoplanets grows, we move steadily closer to answering one of humanity's most profound questions. Whether we discover abundant evidence of alien technology or find ourselves alone among the stars, the journey of searching has already transformed our understanding of planetary systems, technological development, and our own civilization's place in the vast cosmos. The Silurian Hypothesis reminds us that scientific questions, no matter how speculative they initially appear, can lead to fundamental advances in our understanding when pursued with rigorous methods and open minds. The search for ancient civilizations on Earth may have yielded no evidence, but it equipped us with tools and perspectives essential for the next phase of humanity's greatest adventure: the search for intelligence among the stars. The Silurian Hypothesis started as a simple thought experiment. Could we detect ancient civilizations on Earth? While scientists found no evidence of previous technological societies, this research revolutionized how we search for alien life. We now understand that industrial civilizations leave subtle chemical fingerprints in planetary atmospheres that could be detectable across interstellar distances. Our own civilization is creating signatures, from atmospheric pollution to artificial lighting, that will remain visible to alien astronomers for millions of years. As we develop more sensitive telescopes and detection methods, we're moving closer to answering humanity's biggest question. Are we alone? The search for ancient Earth civilizations taught us that even negative results advance science, giving us the tools we need to explore the cosmos and potentially discover our cosmic neighbors among the stars. Whether we find alien technosignatures or confirm our solitude, the journey itself has transformed our understanding of planetary systems, technological development, and our place in the universe. The universe may be vast and silent, but we're listening with better ears than ever before.